So yeah, welcome everyone. I'm going to talk about multiplayer games and collaborative editing with Phoenix LiveView. As you might know, there are two main use case scenarios for which Phoenix LiveView is intended. One is to, if you already have some kind of mostly static web application, use small snippets of LiveView to add snippets of interactivity to it. For instance, to add auto-completing suggestions to a search bar. Now, as these snippets are usually very self-contained and simple, this is not what we're going to talk about today. Already a lot has been written about this. What we are going to focus on is how to manage a single page application using LiveView, where essentially the whole user interface a user sees in the browser is rendered using LiveView. And the idea of this presentation today is to go beyond the simple chat or to-do application examples that other getting started tutorials often use, to talk about what happens when a single page application written using LiveView grows over time and how to keep it from becoming complicated when it becomes more complex. I'm hoping to answer or at least contextualize some common questions that people have when they start using LiveView. And we're going to tackle this by actually building a small multiplayer game today. Now, why am I talking about this? Well, I've been working with Elixir and Phoenix now for roughly 4.5 years, doing mostly a lot of web development, although also some other things. And most of these web applications are actually real-time systems where multiple users interact with the same thing. One of the projects I would like to focus on for a little bit to give you an example of where LiveView really is very useful is what I'm currently working on with the company LiveView, which focuses on building hardware and software to manage video streams of live streams of video cameras. This is one of their devices, a color correction unit. Here in the back, you can insert up to 4 different video cameras of different brands. And then if you have this nice extra hardware board, you can configure the exact settings to make sure that the colors between these maybe very different cameras that hang in different locations all look similar, so you have a coherent image. Now, of course, you might have such a board in your studio, but these kinds of systems, you have many cameras hanging around, for instance, a soccer stadium, or maybe around a race track or a long cycling track. And it's important that not only do people in the studio have access to these settings, but also people handling the cameras in the field. And so there also is this interface, which we built using LiveView, that allows people to actually configure this on their phone or iPad, or maybe a tablet, or maybe on their computer. But it's very important with the system that users are immediately notified of each other's changes to make sure that people do not override each other's changes or apply the same correction twice. And these kinds of systems are where LiveView really shines, where we have some kind of application where multiple users or multiple devices or tabs of the same user need to see and edit the same underlying state representation in real time and be updated, be notified about changes other users make in real time. And this is what I call, collaborative editing. There are many systems out there where you see this used to a very high degree, for instance, Google Docs or other cloud shared editing tools. But many interfaces out there would benefit from users being notified of each other's changes immediately to make sure people don't override each other's changes. Now, of course, how important this is, how much of a problem it is when people do override each other's work, very much depends on your particular application. But this is where I think LiveView is in its element for single-page applications. And game development also very much falls in this category, because a multiplayer computer game also is a system in which multiple users are manipulating the same underlying world state according to the rules of the game. And so therefore, this is also a kind of system for which LiveView works very well. Of course, there are a couple of caveats, because LiveView has a bit of extra latency and because it cannot do all the kinds of super fancy rendering in the browser. It can't be used for games where you have this very hard real-time requirement where people would immediately lose if another player's internet connection would be slightly faster, for instance. But for other types of games, for turn-based games or games that are real-time, but it's not as important that your latency is super low, Phoenix LiveView can really be used and is very easy to use. And I have been part, as one of my hobby projects for the past 6 years, of a group of friends where every year we take part in the so-called Global Game Jam. And this is an event where in 48 hours of time, you start completely from scratch and together implement a small computer game. And then at the end, everyone tests each other's games and they are rated and there are some prizes. But the idea here is that you very quickly develop something simple based on a theme you only hear once this event is started. And this game that is shown here in this little video example is what we built in 2018. This was still before LiveView was released. This was using Phoenix channels directly. But here you have this game that actually runs on this large TV monitor. But people that were walking around the room could join into a running game at any time with their phone by scanning the QR code and then use their phone as joystick for their player character on the screen. And it was absolutely amazing for us that it was so easy to set up such a system using Phoenix channels back in the day. And if we had been using some kind of other technology, we probably would have not finished, or at least would have not gotten this far during those 48 hours of time. But first, let's look at a little bit of foundation of what Phoenix LiveView does, how this is different from other single-page application systems, especially with the real-time requirements. Now, in a vanilla application where we don't use Phoenix LiveView, but depend on some other kind of systems, have other kind of libraries, maybe we write it directly in JavaScript, maybe there's some other language that compiles to JavaScript. But in any case, if we want to add this real-time idea of the browser sending events to the server, being notified in the background, even if we're only talking about, for instance, AJAX requests, then suddenly we have a lot of complexity to tackle. There are all these different things that we need to manage, both on the browser side and the server side. They're very closely connected, but most of these things actually are only tangentially related on what we really would like to do in our application. Actually, this is not even the full list because it's only the happy path. Proper error handling and graceful reconnection are also things you should handle correctly. However, these are, of course, the things that are immediately left out if your deadlines are too strict. But for most applications, what we actually really care about is handling the events when the user clicks on a button or something. And then after we update what that means for the underlying shared state, then we want to interpret how this would change what the user sees in their interface. And these two green parts are the only things that really are interesting for an application. And all the rest is incidental complexity that suddenly you also have to care about. So the core idea of LiveView is the realization that if you move the second step, the interpreting or rendering of the changed state to the server, then suddenly all the transportation logic, the connection handling becomes completely generic across all possible applications you might want to build. And therefore, this can be abstracted away, and that is what LiveView gives you. Now, the other nice thing is that how these events are actually handled is structured in a very normalized, well-defined way, which is known as the simplified version of functional reactive programming, or also under the name the Elm architecture. And you might also know it as essentially what all other OTP gen server-like processes do anyway. And the Elm architecture was also very much based on what Beam processes do. And if you are starting out just now with Elixir, you don't yet know what it means. Let me show you how this works in detail. The idea is that we start with some initial state, and then every time an event comes in, be it from the browser or maybe just from another process in our Elixir LM cluster, then we call a callback function, which is handle event, or sometimes handle info, handle call, handle parents, depending where the event comes from. But the idea remains the same, namely that using the current state and this incoming event, we transform the state and return a new transformed version of the state. And this is how we handle a single event, but we can, of course, repeat this as many times as we want. And if we write our code this way, it becomes very easy to reason about how the state transforms over time, rather than having callbacks all over the place, which is how you would do such a thing in certain other systems. Now, this is exactly how normal Elixir processes work. However, the little bit of icing on top that simplified functional reactive programming adds is this extra callback render, which takes the current internal state and transforms it into something that's interesting for the user to see. And that's the core of how LiveView works. These two parts are what you need to care about as a user, and the rest is completely abstracted away. And in this way, we can get away with writing virtually no JavaScript, and we have this very structured way of handling events which makes LiveView processes very easy to test, even without setting up a complete browser stack. And it's also very easy to integrate these processes in an existing Elixir airline application. Now, of course, it's worth mentioning that because everything is on the server, LiveView cannot properly work if you have a bad connection. And another problem that you might encounter in certain cases is that because LiveView renders the resulting state all the time, and it does some nice tricky work under the hood to make sure the still is very efficient, but because essentially what we end up every time is an updated DOM, HTML parts that do not work with a DOM, such as working with an HTML5 canvas, having WebGL, using the user's webcam, those kinds of things cannot be interacted with directly from LiveView. And other things might be too slow, for instance, animations, but we can get away with just animating those with CSS. Now, finally, there are some features, some events you would like to trigger that are still missing. LiveView, of course, is in beta, and a lot is being added, and you can always add a tiny bit of extra JavaScript if you really require something today. But now let's talk actually about the architecture of LiveView when we're talking about a more complicated, or more complex single-page application system where multiple users try to interact with the same underlying state. Let's actually talk about building a game. This is the basic idea of a single running LiveView process, where internally we store the state that is only part of, well, this user-specific state that is specific to the particular browser session, and that, of course, is connected to the user's browser. Now, if we want to work with shared state, what we change here is that we add the second layer behind it with the shared world state. And every time the user actually triggers some event that is not specific to this user session, but actually tries to manipulate the shared state, then the local LiveView process will forward this request to the shared world state and get some kind of response. And in this way, if we add multiple users side to side, they can all interact properly with another. Now, this is still a little bit vague, and that's with purpose, because this backend thing can be just another Elixir process, but it could also be built in a different way. Maybe it's just a database with some extra Phoenix PubSub next to it, so you're also notified when things get updated by a different process, or maybe it's actually written in a different language that lives outside of the beam, and you have some messaging queues, or maybe you use Redis, those kinds of systems to coordinate between your locally running LiveView processes and that other system. Those things are all possible. In the end, the only requirement here is that the local LiveView processes in some way communicate events to the shared world state and get some response back. Now, the particular game that we are going to build today is called Agar X, and this is a variant, a simplified version of the very famous game called Agar.io. The idea here is that all the players in this multiplayer game are cells living on a petri dish. They can move around their circular cells, and they can eat agar, which I learned is this jelly which makes cells grow very rapidly. And they can also eat each other. A bigger player can gobble up a smaller player, and then when you eat something, of course, you get bigger and bigger and bigger. And every 3 minutes, we reset the round and start a new round, and we keep track of the high scores. Now, you can already go to the link there. Also, in the Q&A section, I've already posted the link there as well. And in a couple of slides, we will also try this out ourselves during the presentation. But it would be very cool if you already would join and test it out. Now, I want to briefly tell you about the actual game logic. But most of the rest of the talk will, of course, go more in detail about the LiveView parts. The game logic itself receives from these LiveView processes, in this case, regular OTP messages. But when itself is updated, it sends back the updates using Phoenix PubSub. And in this way, the game server doesn't have to keep track of processes that are listening to it. And we're using a trick here, which is very commonly used in Elixir when a process needs to do something in a given, well, regularly every couple of milliseconds. Then we just send the process itself a message every couple of milliseconds and handle that message. We have only one of these processes in our current single running Elixir node. Of course, you can easily change it so that there are multiple rooms, multiple games running at the same time. Yeah, when we initialize, we already schedule this message for later. Then we return some initial state with the current time. And then we handle this message that arrives every couple of milliseconds, immediately scheduling the next, and then actually keeping track of the current time versus the previous time, and running here in state.tick the actual update of the game logic. By separating it this way, we make sure that the state itself doesn't care about time and the flow of time, which makes it easier to test. The reason we pass in the delta time, by the way, is that Elixir processing scheduling is not exactly strict. It might take slightly longer than these 30 frames a second, which means that we need to make sure that we keep track of how much time has actually passed to make sure that our animations, that when players move around, that this animation, this movement is fluid. Now let's actually talk about the state, both the internal state in this particular Gen server, but also the state in the different LiveView processes. You can use the same patterns here. Of course, if your shared state is written in a different way, if it's in a database, for instance, you might use a very different pattern. You might use Ecto with domain-driven development as an example. But if we're in the Elixir Gen server-like world, I have these three tips, these three general concepts that might help here. And they go from easiest to add and least buy-in that you need to the bottom, which takes more work to add, but is results in something that is super normalized, super compartmentalized, so you have a very high separation of concerns. So it's important to note here that you can add these things gradually as a project is growing. You don't have to immediately do all of these things on a project that is just starting out. Yeah, so for the first point, if you want to store more complicated state inside a LiveView process or inside any Gen server, I recommend using a nested tree of structs, or what's also known as using product types and sum types, or if people really want to get fancy, using algebraic data types. But all those things really mean more or less the same thing, which is that you specify very clearly what kind of fields you expect your structs to have. And in this case, we have a world struct at the top, which just keeps track of a list of players and a list of Agar jelly locations. And then at the bottom, here's what a single player would look like, with a name, a size, a position, and the direction that they're moving in. What's also very useful, besides the nested structs, are those sum types, and that just means that a particular field could have one of multiple values, but no more than one of these values at the same time. For instance, something might be nil, or actually a player, or something might be okay, or an error. Those kinds of situations. A lot has been written about sum types and product types. There are a lot of guides to find out there to help with this further. Now, we use this idea not only in the state of the Gen server, the global game server, but also in the local state. Here, in this case, we compartmentalize it this way by having this general local state that keeps track of the lastly seen game state, as well as what keys the player is actually pressing and who the current player actually is. But actually, how the keys are pressed and how this is translated into what direction the player moves in, that is handled by a separate module here, the controls module you see in the bottom. By separating these things this way, we make sure that every module really has a single concern. As for the second point, nested event handling. The idea here is that rather than ending up with a Phoenix LiveView module, which has tens or 20 or maybe 100 different cases of your function classes, of your handle event, handle info, etc. functions, we normalize the events regardless of where exactly they come in from. And then we might even say that we split this incoming event string, this topic string, into multiple parts based on slashes, or some people like to use colons instead. And then this is a convention, pick one and stick with it. It doesn't really matter which one you pick. And then the actual state handling is done in those modules, which I showed you just now. The idea here, oh yeah, and then of course the final step is actually, after everything has been updated, storing it in the LiveView process, just as before. But the idea here is that the state handling actually lives right next to the logic of the structs that it is transforming. In this case, for this local state, we if the event topic starts with controls, then we know that it is actually interesting for this controls struct that we have nested in here. So we dispatch it to there and only put the result again in the correct place. But if it's the game tick thing, yeah, well, we can handle that one directly. Essentially, what we've done here is reinventing a very simplified form of routing, where from the outside in, modules mostly only care about where certain event topics are dispatched to, and then on the bottommost layer, that's where we're actually like, oh, this is an event that takes that happens with our player, so we do this here. And that compartmentalization gives you a lot of flexibility in how and where certain events are handled. Now, the third point goes yet another step further. The idea here is that we not only have this nested state and nested event handling, but also we try to reduce the number of side effects that we are actually performing while updating our local state. The goal here is to keep our code as maintainable as possible and as flexible as possible, where we split apart what we want to do and how this actually works, like how this is actually implemented. So we declare somewhere, for instance, that we want to now send a player movement thing to the global server, or that we want to redirect to a different page. And then only after the local state has been updated, then we run that effect. And of course, we might have a list of multiple of those effects. And the cool thing about doing this is that it's much easier to test than if you have these side effects or effects where processes are broadcasting to other processes or interacting with the database. Because for those kinds of, if your system is written in that way that requires this, then in your test suite, you need those other processes or you need that database to be available as well. That slows everything down. So here's an example. I usually write some kind of simple helper function, an effectful update in, which works just like the normal update in that lives in the kernel, with the difference that every result that we get from the function that we have as parameter is supposed to return a tuple with both the resulting struct and the effects that we might want to run. And then the effects are returned directly and the struct is put back in its place of it in its nested accessor location. Now here in the bottom, you see a possible effect where we say, hey, we want to broadcast a player movement. There are many different kinds of effects that you might want to come up with. And there's a sliding scale here. You could also just have an effect that says, hey, I want to do a Phoenix pops up broadcast. And that already gives you a lot of flexibility. The more fine-grained that you get in here, the more code you need to write. And there's some diminishing returns there. But the main idea is that, of course, your event handling logic becomes slightly longer. But this way, we can make sure that we do not actually need the socket, access to the socket, for instance, within our event handling, nested event handling logic. And we can have these effects locally and then have somewhere else an effect interpreter, which actually performs all these effects based on the list of effects that you end up with. And in the test suite, we might have an effect interpreter that does absolutely nothing, or we might have an effect interpreter that, for instance, rather than writing to the database, writes to an in-memory map, which is also much faster. Now, a fourth thing, which I want to briefly mention as an addendum, is that you can also, on top of this, it doesn't really matter in which combination with the other three things you use this, but nowadays there are a couple of libraries. I'm working on TypeCheck. Another library that has been existing for slightly longer already is Norm, where you can add contracts to functions which prevent input being sent that the functions know they cannot handle, but also at the same time, from those same specifications, allow you to create property testing generators where you take the inverse, namely that the function is able to handle all possible valid inputs that it says that it can expect without having any problems. And by adding this, you get a lot more confidence that your state handling logic works correctly. Of course, if you want to add this to an application, it is important that actually calling those different state transformation functions is relatively fast, which is one of the reasons to separate those state and effect things to make sure that we don't have to call the database in the meantime during a property test, because you're expected to run, for instance, 1,000 test cases with different inputs. And if you need to call a database in the middle there, then that is the difference between running 1,000 cases in a 1/10 of a second versus taking 10 or 20 seconds. Now, one final thing to talk about, which is not a bit of a different topic related to the more purity changes, which I talked about just now, is how to actually render the front end and how to split up a LiveView process maybe into multiple parts when things become more complex. And there are two problems here, or two problems. There are two common questions. The first one is, should we, if we have some nested stuff, should we add another LiveView or should we use a live component? And the other one is, should we use stateful LiveViews and live components or rather stateless ones? Well, the second question is actually a lot easier to answer, which is use stateless things as long as you can and only move to stateful if you find out somewhere that it really makes your code a lot simpler. Because for stateful processes, you can encapsulate really the interactions the user has internally, and only on the outer layer have much more high-level events and responses that you send back and forth. As for using a LiveView versus a live component, well, a LiveView is an extra process, and this both has advantages and disadvantages, because it does give you extra fault tolerance, and it does mean that it is completely separate in what kind of server-side events it can accept. However, it's also slightly slower, so I would usually suggest that if you don't need it, don't use it. If you're just wanting to have some HTML that you want to reuse in multiple parts, and maybe have some extra helper logic in there as well, so some helper functions, then just use another live component. Now, one final thing before we are actually looking at the game that I want to mention is I was super impressed by the presentation of Rafał Studnicki yesterday about visualizing software complexity. And so I decided to take his graph creation procedure and run it on this application, this example application that I've built. And this was the output. And I've color coded here the different sections of the graph because, of course, the module names are too small to read. But here the yellow part, that's actually the internal state of the global game server. The red parts, those are all the different components and LiveViews rendering on the front end, which are, of course, because the components are nested within the game LiveView, are connected. And the other parts, the green lines, well, those are actually the real connections between different parts of the application. So the main connections you see here are from the game live, which is the main LiveView process, to the global game server, as well as to different implementations or different particular effects that are used internally. And personally, I think this graph really shows how much decoupling you are able to achieve. Of course, you can go even further than this, but I thought it was really nice to test this out. All right. One final thing I want to mention before we actually are going to look at this example. And that is, well, of course, there are a couple of other things that I implemented in my example application, which I don't have time to go into during this presentation. However, while it is conference-driven development, which means that some parts are really fleshed out and other parts, such as, unfortunately, testing isn't in there yet, I really hope that my application can serve as an example for people to see an example of a slightly more complex LiveView application. And please ask questions, post issues on the GitHub repository, and I will try to explain my reasoning and maybe update it even a bit more in the next couple of days or weeks. Okay, now let's look at the game actually in its full glory. Obviously, this is the moment there's some Wi-Fi problem, but you're still connected through Ethernet. Here we go. And now I have my mouse back. So yeah, we can. This is the main screen, and we can add. Enter a username here. Some people are already playing, which is super cool. We can join this game. Now, of course, on my computer, it will probably be slightly slower or laggy because I'm also running the video rendering and the presentation in the background. But if you run this yourself, you will see how well it is able to work and keep up with multiple users. And you see that you can move around and eat these small green dots, and that you're also able to. Here we go. I'm probably being eaten by this beautiful cat face in a second. Yeah, there you go. And then if you lose, you get redirected to the home screen. And every couple of minutes, we reset the game state and keep track of all the scores. Yeah, so feel free to tinker around with it and let me know how it goes. Some extra resources to think about when you're using LiveView. Be sure to read the full documentation of LiveView because there's a lot of interesting stuff in there. Including there are more and more advanced features that are now being added with new versions. I'm super excited to hear what Chris is going to tell us in the next session after this one. There's also a book which is going to be released soon. I'm very interested and eager to see what Bruce Tate will actually tell us about LiveView in there. Then there's also a video course, which is a paid one, but it also seems to be very good. One thing I did mention here, there are also a couple of very good guides on how to structure your structs in a way that works with this nested tree of structs or algebraic data type ideas. I will link those as well in the Q&A section after finishing the presentation. All right, that's everything I had prepared for you today. And thank you very much for your time. And I would love to answer all your questions.
Thank you very much for the presentation, Wiebe. So I can see on Hoover that we have one question besides the ones you have made yourself. Let's see. So I don't know if Heiko wants to take the microphone and ask his question.
Yeah, I would like, yes. Can you hear me?
Hello. Yes.
That's nice. Yeah, I'm thinking about using Norm and the type check library, and I think I heard you use them, and would be interesting to hear where you use them in your game.
Where I use them in a LiveView application. I mostly use them to type check the handle event function, and of course also type checking the shape that the different structs themselves have in the application. And in this way, you can make sure that really the handling of this handle event function works correctly, even if many different events happen after one another, and that we still end up with a consistent state without anything crashing. And that's a really cool place. That's the location I usually use property-based testing. And then besides that, what I also do, and usually I use some unit tests for that, is I add contract specifications to the handle event and handle params functions of the LiveView process, so in the LiveView module itself. And that way, if in my unit test, I then check whether a particular event is fired when I click a button, for instance, then I immediately get a crash if the event that is sent from the HTML page, so that is configured in the HTML that's actually being rendered, doesn't match the input, or is not in the list of events that the state modules say that they expect. And in this way, you can also make sure up to a degree that all the events that are in your HTML are actually events that your application knows how to handle. Thank you. Great question.
So does anyone else have a question? I guess the first one to steal the mic and talk is the winner.
Yeah, Sandesh here. People had asked a few questions yesterday about in AML, LiveView AML. What you have shown is a really nice example, and I really appreciate it. Very nice example. this answers question very. Your example answers many questions about LiveView.
Thank you. Thank you. I'm very happy to hear that, because of course, at some point when you're building something like this, you end up a little bit in this echo chamber where you hope that what you're building, and mostly the presentation, hope that what you're presenting is something that people can follow. So it's wonderful. Thank you very much to hear that.
Yeah, and I guess even if Chris McCord presents something that will change everything, the strategy of separating the side effects and the event is so strong, and I have used it in other applications that were not LiveView specific, but it is really, it makes stuff easier to test, very easy. And so, do we have another question?
Have you tried using any external thing like game engines or any OpenGL or something with LiveView? WebGL?
Yes. Great question. Actually, the example I showed all the way in the beginning, which we built using the Global Game Jam, that predates Phoenix LiveView, but we ran Phoenix channels, so the basic WebSocket connections on the phones of the people in their phone web browser. But then the game that you saw on the big TV screen there, that was programmed in the game engine Unity. And there was a TCP connection in the back, connecting Unity also to the Phoenix server to make sure that all the different user inputs of the players were forwarded and seen correctly.